Okay, thermal radiation, which is our last topic today, is very complicated. It's much more mathematical than our previous two ideas. And when we talk about it in heat transfer, it's a time where students start thinking, "Wow, this can be complicated." It deals a lot with there's a lot of integrals that's introduced here. Just a little bit more math. But again, we're going to talk about this in a little bit more simpler form. But let's talk about what thermal radiation is. First of all, it's energy transported by electromagnetic waves or photons. Unlike convection, or conduction, radiation requires no medium. And can take place in a vacuum. Now, just because it can take place in a vacuum does not mean it must take place in a vacuum. Thermal radiation is happening all around you. If any two surfaces, any two things have a delta T, there's going to be thermal radiation happening here. Students have often asked me, Dr. Wanklund, how can snow melt in the middle of a winter when it's 25 degrees Fahrenheit outside? That's well below freezing. It's still melting. It's because of thermal radiation. How can you maybe live in a basement apartment? Your basement apartment in the wintertime, you might have it at 75 degrees, yet you're still feeling cold and chilled. That's because you are exchanging thermal radiation from a cold window or a cold wall. Same way in a warm summer, you might feel the thermal radiation coming from a backyard fire if you're out with one of these fire pits or something like that. So thermal radiation is a thing. Now, it's important here we consider radiation. I was talking to a friend who was dealing with making aircraft circuit boards in a smaller company, and they were trying to figure out how to cool their boards. They just usually put a heat sink on the top of it and let air is enough, just natural flowing air over that is enough to cool down the chips on their board. However, they were developing this new board that was going to go at high altitude planes, and as you go higher altitude, now you're not going to have as much air around. In fact, you could get to the point where you go out of the atmosphere, and now you're in a complete vacuum of outer space. And even though it's very cold up there, you can only exchange heat through radiation. So we have to think about radiation and how that interacts with us. So we have to understand radiation. So solids, gases, liquids. Here, I should put this here. Solids, gases, liquids. They all emit, absorb, or transmit radiation to varying degrees. Okay. Now, there is a special type of body that we talk about in thermal radiation. It's called a black body. A black body is perfect. So when we're studying thermal radiation, we are going to consider this perfect black body as being the perfect emitter and the perfect absorber of thermal radiation. That's what we'll base all of our discussions on. How are they related to a black body? That's that perfect idea. But what we're going to talk about here in thermo is we're going to talk about a gray body. So a gray body And what it's saying here with the gray body is that its emission equals its absorption. So we're going to say epsilon equals alpha. That's what we need to talk about. Epsilon is emission, absorption is going to be alpha. So we're going to assume this. This is an assumption that we make. Okay, and you know what that does? That vastly simplifies our class, or our understanding in this class. So you may not appreciate that, but that's a really a big assumption that really changes the way we look at things here. Let's look at the law that helps us understand thermal radiation. That's the Stefan-Boltzmann law. Okay, so how we do this is we're going to look at the surroundings. This could be anything. This could be a building, a wall, the atmosphere, the blue sky, the surroundings, and we have our surface here. Okay, so I'm going to call the surroundings that are going to have a temperature Ts, and then we're going to have a surface here that I'm again going to call TB. Again, so I don't have to call it surface and surrounding. I don't have to mess with that. And we're going to see that radiation can come in here and it can be absorbed. It can be, this is going to emit. It can absorb and emit at the same time, and it also can let some of this through. It can transmit. Okay, it can do all of those things all at the same time to various degrees. But again, we're saying we're dealing with gray bodies. The absorption and the emission is the same. So if I want to look this and I want to say what is Q dot radiation emission? Okay, that is going to equal the epsilon, which is the emissivity, times the area. This is going to be the surface area, times sigma, and I'll talk about what sigma is, times temperature of the base to the 4th power. Okay, so this is very important here. This is what's emitting, or this is, I should say, out, leaving the system. Well, what is this sigma that I'm talking about here? Sigma is equal to, this is the Stefan-Boltzmann constant. And it is one of those interesting constants that has a really nice number when SI. So at SI, sigma is equal to, and it's really fun. It's probably the funnest thing about nuclear engineering that we have here. 5.67 times 10 to the minus 8th watts per meter squared Kelvin to the 4th. Okay, and in English engineering units, just like everything with English engineering units is not as fun, it's 0.1714 times 10 to the minus 8ths BTUs per hour per foot squared per Rankine to the 4th. Degree Rankine to the 4th. Now the key thing is here is this is now a temperature to the 4th. And radiation requires that your temperature be absolute. So this, I'm going to say this one must be absolute. Because a temperature Celsius to the 4th is different than the temperature Kelvin to the 4th. A temperature Fahrenheit to the 4th is different than a temperature Rankine to the 4th. So you must have them in absolute here. Okay, that's a very important difference. In conduction and convection, because you're just having a delta T, doesn't matter. Here it does matter. It matters very, very much. So be taking care of that. I should mention the emissivity of a substance is going to go between 0 and 1. 0 means it's not emissive at all. 1 means it's perfectly emissive. Somewhere in between there is probably where we're going to be. that's going to be what we have coming out. If I wanted to find out what Q dot radiation absorbed is, or in, that's going to be alpha, area, sigma, temperature of the coming in from the surroundings, so it's surf surroundings, to the fourth. So this is going from the base. This one here is coming from the surface out. This is coming from the surroundings in. The only difference here is this is going to be the absorption. And this number is also going to be between 0 and 1. Everything else is going to be the same. So if you want to look at the net radiation, which we often do, Q dot radiation net, what you're going to do is you're going to take Q dot in, or I should say Q dot out minus Q dot in, and you're going to get this: epsilon, sigma, area, temperature of the base to the fourth, minus alpha, sigma, area, times temperature of the surroundings to the fourth. And in our class, we are going to say that if epsilon is equal to alpha, we're going to write this as epsilon, sigma, times area, times temperature of the base to the fourth minus temperature of the surroundings to the fourth. And that is going to be our net radiation that we're going to deal with. Again, no, this is the surface area. Know that these temperatures must be in absolute. Okay, know all those things. Know that this is going to be between 0 and 1, and know that this value of sigma is going to be given to you on your equation sheet, so you don't have to worry about that. Okay, now this, we will end talking about radiation here, and then I have one more thing that I want to mention to you as we end this lecture.